My name is John Fowler. I work in Vehicle Systems Analysis at the Marshall Space Flight Center, and I'm the task lead for Ares 1 liftoff clearance. The preliminary analysis that was performed very early on during the Ares design, around the PDR timeframe, demonstrated that the vehicle could possibly impact the launch tower during liftoff. To understand that, you have to realize that the Ares vehicle has a tower near it that is used to service it prior to liftoff, and it's fixed. It doesn't move after that servicing, so while the vehicle is rising during liftoff, you have to avoid running into this tower. The environmental conditions affect that to some extent. Sometimes they're a favorable combination of environmental conditions, and the vehicle will actually drift away from the tower. They help you. In other unfavorable combinations, they'll cause the vehicle to drift toward the tower, and in some extreme cases will perhaps actually contact it. So the job was to try to overcome the environmental factors and the vehicle behavior so that we prevented contact with the tower during liftoff. One example of an environmental factor is the ground winds. They were the primary driver from an environmental standpoint for liftoff drift on Ares 1. The vehicle is fairly large and presents a fairly large projected area. It's affected by the wind, and if the wind is from a favorable direction, it'll blow you away from the tower. If it's blowing toward the tower, it tends to blow the vehicle into the tower. So that's one example of how an environmental factor can factor into the liftoff drift. An example of a performance parameter that affects liftoff drift is thrust misalignment. And it's fundamentally where the line of action of the thrust, or where the nozzle is pointed, is not aligned with the center of gravity of the rocket. And it creates a different flight path than you would like. Ideally, for liftoff drift, you want the vehicle to rise completely vertically and without any drift. But when the thrust is misaligned with the center of gravity, it tends to drive the vehicle off that ideal flight path. That is actually an error that can result. It's a very large system, and it's very difficult to precisely have the nozzle pointing at the geometric null point where there is no misalignment. So it's a vehicle characteristic that happens during flight to varying degrees, and it's something that we had to account for in the analysis. But that is an example of a vehicle tolerance or error that drives liftoff drift. The risk statement for liftoff clearance risk is that given the current requirements and the latest analysis for liftoff drift, there's the possibility that the Ares 1 may contact the tower during liftoff. And the consequence of that ranges from damage to the flight hardware or the ground system all the way up to loss of crew. The mitigation plan primarily revolved around analysis. The early part of the first steps that we performed involved analysis to uncover the sensitivities, to identify the major drivers behind liftoff drift. Once we understood the major drivers, we began to evaluate potential solutions. There were solutions involving changes to wind conditions, also vehicle features that we could add, flyaway commands to essentially steer the vehicle away from the tower. We looked at each one of those to understand the pluses and minuses of each. What we found from that is no single solution was adequate to overcome the problem we were facing or to mitigate the risk. So at that point we began to do further analysis where we combined these solutions together to try to get the proper clearance. And once we converged on the most effective combination, then we had to go back and look at the entire analysis again to not only confirm that we had the clearance that we needed, but that we were within the vehicle capability and we didn't cause a problem for the ground system in terms of plume angle and those kind of things. Ares 1X was helpful in the Ares 1 liftoff clearance mitigation in that it provided a real-world trial of the use of a flyaway command and to judge how effective it would be in the real world. We had a lot of analyses. Ares 1X offered a chance to really try that out and see how effective it was, as well as to give us a way to assess the impacts on the ground system as a result of having a flyaway. Turning the nozzle with a command is nice in that it moves the vehicle in a path that you desire, but it creates some plume impingement on the ground system that can get to be a problem. So that flight test was very advantageous to us in that it confirmed the effectiveness of a flyaway command. They introduced a command very similar to what we have on Ares 1. It was effective at providing clearance, and then we also were able to see the after effects on the ground system and understand how those would affect the ground system for Ares 1. One of the things that was helpful for us on the Ares 1 risk mitigation is that part of our team that were really tasked with developing the flyaway maneuver actually developed the flyaway maneuver for Ares 1X. So they had a lot of experience, a lot of analysis already behind them when it came time to look at the differences between the two vehicles and change the flyaway. We were able to take advantage of the lessons learned from Ares 1X on Ares 1. And it also provided almost a seamless integration when you had the same people performing the same function on both these projects. It was very easy to maintain that knowledge and transfer it from one project to the other. The solution that we converged on was a combination of three things. One, we executed a flyaway maneuver to steer the vehicle away from the launch tower. The second thing, we instituted an anti-drift controller as part of the flight control system, and that would help to limit the drift as well and supplement the flyaway maneuver. And then the final thing is we reduced the wind requirement from 34 knots from the south to 20. And that not only provided a measure of clearance, it provided a significant margin in addition to clearance, as well as mitigating any plume concerns that the ground systems folks had for the launch tower. The anti-drift controller is a subset, if you will, of the flight control system, the flight computer. And what its function is, it takes sensor input. There's sensors on the vehicle that can detect the movement, and in this case, drift, lateral displacement. And it will issue commands to the thrust vector control system that steer the steering wheel for the rocket, if you will, that steers the nozzle, to attempt to overcome that. And we use that in combination with this flyaway maneuver to address some of the timing issues that arise when you're looking at the liftoff period. The whole thing for us is over in about 6 seconds. When you fire the motor and the vehicle comes off the pad, you tend to get out of shape very quickly, so we need the combination of these things to be able to catch up and steer the rocket away from the tower. One of the lessons learned for me as a part of the mitigation of this risk is that when you have an integrated problem, you have to have an integrated solution to it. While this was a vehicle-centric risk focused on Ares, there were at least a couple of other major stakeholders that were very interested in how we mitigated this risk. One of those stakeholders was the ground systems project at KSC. They had a very mature mobile launcher and tower design. They were well down the design path. They were very close to actually going out on procurement for construction of the mobile launcher. So they were very sensitive to any changes to that design that might be driven by the vehicle behavior and trying to mitigate this drift. The second major stakeholder that jumps out is Level 2. Level 2 had a lot of interest in liftoff clearance and vehicle drift during liftoff, but one of the major things they were interested in is the vehicle state during this period and how it might affect the ability to perform an abort with Orion. So the lesson for me was to involve ground systems as well as Level 2 in the actual decision making process that we went through. When we talked about the mitigation plan and selecting the solution, I made sure that ground systems and the Level 2 representative that we had were a part of that decision making process. That did a couple of things for us. One, they became advocates for this when we were reviewing and approving the solution that we had selected. They were advocates for this solution when it was reviewed within their organizations. I didn't have to sell it. They sold it for us. And the same thing with Level 2. As we began going through their reviews, the Level 2 rep was a part of the decision, and he helped sell it. So that streamlined the review process, and it minimized the chances of any second guessing from either one of those stakeholders down the road after we had selected the solution. Another lesson learned for me as a result of going through this process is that if you design the ground system before you design the vehicle that it supports, that's a recipe for trouble. And that's essentially what led to this risk for the vehicle being created. A little background is that the ground system were tasked with designing the launch tower ahead of the vehicle design. And so it was much more mature. They were much further down the road. They knew a lot more about their design and were very close to actually building the hardware before the vehicle design and its behaviors were very well understood. They based that design on some extrapolated shuttle behavior. That proved to be unconservative once we were actually doing a real analysis of the Ares 1 vehicle. And that's what created the situation that led to the risk, which was where once we calculated the real drift with the Ares 1 vehicle, it was very close to the tower and in some cases running into it. So for me, the lesson is that when you're designing two complementary systems like that, you need to evolve them at a reasonably consistent level of maturity so that you don't know a lot about one and a little about another, and the lack of knowledge on the one becomes a threat to the other. And that's exactly what happened in this case. But look at it from an overall standpoint. And it took all of those perspectives to identify this solution. If we'd have let the Ares team run off and do it on their own, we would have probably came up with something that was good for the rocket and bad for the program. And the same with any of the unique perspectives. The secret was coming up with something that made sense to all of us. And that's really the takeaway for me, is that you need to take the time to do that. It does require more time than running to the obvious solution and latching onto it and saying, this makes sense for me and I really don't care if anyone else likes it. Here it required an integrated solution. It took a lot of patience, which was a lot to ask from me. I'm not a patient person. But I'm glad we took the time to find that solution that made sense from an overall perspective. If you're interested in more information about Ares 1 liftoff clearance, I'll be glad to discuss that with you and provide any information I can. Or you can contact anyone in the Vehicle Systems Analysis branch here at Marshall Space Flight Center.